Okay, it's a great pleasure to introduce Abie Flaxman, who's a professor in the Institute for Health Metrics and Evaluation, and he'll be telling us about anticipating differential privacy in the 2020 US Census.
Thanks so much, and thanks everyone for coming. As Anna said, my name is Abraham Flaxman, or Abie for short. I am at the Institute for Health Metrics and Evaluation here at UW. That's in the Department of Global Health Metrics in the School of Medicine. But I used to be sort of a theorist. I used to definitely be a fan of a theory seminar. And I encourage you to ask questions and make comments as we go. I like to keep this very much an informal kind of thing, despite having gone over to the School of Medicine and starting to absorb some of their strange customs. I'll give you one custom that I've been getting from my colleagues in medicine and public health, which is a land acknowledgement. The research that was conducted, that I'm going to talk about, was conducted on the traditional lands of the Coast Salish people. I'll give you another School of Medicine custom, which is a disclosure. And this is a way for you to judge, if there's some potential bias from big pharma or other actors in this work. This research was supported by the Alfred P. Sloan Foundation and the National Science Foundation, and other work I'm doing is supported by the Bill and Melinda Gates Foundation. And I also do some consulting work for some of these private sector actors on this bottom line. What I want to tell you about today is the 2020 US Census. And if you've been hearing about this in the news, maybe a couple months ago when people were fighting about whether there would be a question about citizenship on it, you might not have heard the exciting kind of underneath the headline fight about using differential privacy in the 2020 census. And if you haven't heard that much about differential privacy, I'll be happy to tell you about that too, because that is a theory thing. And it's a theory thing that's like, in my time as a graduate student to professor, has gone from not existing to a full thing from theory that's going to be used, which I think is so cool and exciting. And on the other hand, it hasn't made it into like a required multi-course part of the computer science curriculum. So I don't know who's seen a lot of it, who's seen a little bit of it, and who's maybe just heard about it before and not seen too much about it. Wherever you're at, this will be a talk, I hope, with something for you. And so where we're going from census through differential privacy is to bring it all together to how differential privacy is going to be achieved, we think, in the 2020 US Census. And not only how are they going to make things private, but what effect is this going to have on the results that they're going to produce that my colleagues, say, in School of Medicine, Public Health, Social Sciences, are all a little bit nervous about because they rely on this for their next decade of research. Bob?
When do they start doing the census?
They started already.
Oh, really?
Yeah, so the census, the Decennial Census happens every 10 years, and its goal was to count every person in the United States. And their goal really is to say, how many people are there and where are they staying on April 1st of 2020. But because there's so many people and some of them are so far and hard to get to, they have already started counting people in rural Alaska in January. So it's happening. And so I'll conclude just by talking about why I think privacy in the 2020 census might be a good thing for everybody, not just for theorists who are excited to see their theoretical results used in a wide-scale practice, and what is still to be decided, and then bringing it back to you all. What problems might this inspire for you and for us to solve to set things up well for the next decennial census in 2030? Any questions? So I'm going to start with what is in the 2020 census and why might we be concerned about its privacy?
Are you talking about the short form or long form?
Great question. And for those of you who don't know what it's about, I'm talking about the short form. I'll show it to you. It fits on one slide. It's short. And I will allude later to the long form census, also called the American Communities Survey, for which the Census Bureau has no idea how to protect privacy, and to allay the concerns of social scientists, has promised not even to try until 2025. In the short form census, also known as the Decennial Census, there are really not that many questions. The first thing we ask everyone is to print their name, and if they live somewhere else than where they're being recorded, and how they're related to person 1, of which there are 16 choices. For this is person 2. If I was on person 1, there wouldn't be any choices. They are person 1. We then write down this person's sex, a binary choice, and this person's age and date of birth. And then we get into this interesting stuff, but there's not that much of it. Race and ethnicity in the 2020 census will be captured in 2 questions. Is this person of Hispanic, Latino, or Spanish origin? Number 6. And what is this person's race? Number 7. And that's it. Those are the 7 questions to be answered for 330 or so million people on April 1st of 2020. When Census Bureau folks think about what they're collecting here, they think about it in something that they call a database schema, and I don't know what computer science department will think of them calling it a database schema, but it's a table, and it's a table where they're going to say a location for each of these counts, one of 10 million census blocks, which if you think of those as actual blocks is not too far off. And for each of those 10 million blocks, they'll be able to tell you for one of 2 sexes, for one of 115 ages, for one of 126 race and ethnicity categories, which they make out of that question 6 and 7 from the previous slide, for one of 17 relationships to person 1, meaning the 16 that we looked at, or being person 1, how many people fit that description. So that's about 10 million locations times 500,000 distinct histogram cells. I don't know, what are we talking about? 5, 10 trillion values that they want to make a count of. There's only 300 million people here. So when you go through even just which of those numbers are published, because they don't publish all 10 trillion of those, but in something called the Public Law 94 Table 171 book, they publish 2.7 billion of those numbers. In Summary File 1, which includes PL 94171, they publish another 2.8 billion of those. All told, just in terms of the things that they publish because they think people really will actually be using them, we're talking about 7 or 8 billion measured numbers for 300 million people. So like 25 statistics per person, which we're going to get into. They want to maintain everyone's privacy while doing. But what do we do with these numbers? Because you may have been consumers of Census Bureau data and maybe not even realized it before. And this is a good time to kind of like test who's in the audience. Because although this is a theory seminar, there could be social scientists who've infiltrated it. Who, show of hands, uses Census Bureau data in their research?
I've touched it.
And who has read or used other people's research output that you know or think has used Census Bureau data? And who's heard of the Census Bureau before? So yeah, it's a wide range, roughly as I expected. If you ever read columns by the FYI guy in the Seattle Times, this fellow, Gene Balk, really makes a lot of his columns out of Census Bureau data. Here's one that he did recently. He says, for the first time this decade, a dip in King County's white population census data shows. And he's got these beautiful charts that he's put together and a whole bunch of prose that I didn't put on the slide that show the different interesting findings that he's found from, this is the long form census, the one that now is done as a rolling survey, the American Community Survey every year, but the same sort of data that we've gone out, asked a lot of people, from which we can say we believe that from 2017 to 2018, the number of people who are Asian in King County has gone up. The number of people who are white in King County has gone down, and the other race and ethnic groups that he has included in this plot are in between. Now, for people who do use this data, there's a couple of aspects of it that are unique and are relevant because of how they require us to care especially about privacy. First of all, participation is mandatory. When you get something in the mail from the census in the next couple months, it's going to say on this envelope, your response is required by law. You can be fined for not filling it out. No one has ever been fined in recorded history, but you could be. This is not like informed consent human subjects research. This is something that everyone has to take part in. And so as social researchers, when we use this, we need to make sure that we're protecting people's privacy. We are allowed to use it if it's anonymous data, because if it was not anonymous data that didn't have informed consent, that would be not allowed under the kind of human subjects laws that govern human subjects research.
So when you say response is required, is that only the case if you receive the form in the mail? So the reason I'm asked, okay.
Continue.
Right, so like most of the issues that come from underreporting come from people who don't have a static address necessarily, or don't always like reside in the same place. So like in theory, an administration could like fine every homeless person for not. Okay.
Yes, that is one of the reasons why these fines are not enforced. That would be cruel and useless. But the Census Bureau goes to great lengths
I do know that.
to find who lives in every household. Throwing back to that earlier comment about citizenship questions, it's going to be extra hard this time around, I bet. Bob?
How do they handle homeless people?
There is something called the household and group quarters status, and so a lot of what we just looked at is the form that goes to households. There are also forms that go to what's called group quarters, that includes homeless shelters, nursing homes, college dormitories, prisons, and so there's a sort of special extra effort to get people who are not in traditional household residences.
But what if a homeless person doesn't live in any of those things?
Yeah, well, it's always in flux. This time around, for example, people will be able to submit forms electronically. So someone could, for example, go to the library and submit their census information through a library computer.
Do any census people go to homeless places and interview people and so forth, fill out forms that way?
I don't know enough to answer that in great detail, but I will connect it up to where we're going later, because this is getting at the kind of vulnerable populations where protecting privacy is particularly important. And that brings us to unique feature 2 of this data. Besides the ethical imperative to protect privacy and the requirement to do it if we want to do human subjects research on it, it's also law. And you'll hear Census Bureau people talk about Title 13, because that's such an important part of their considerations. And this is the United States Code, Title 13.9.2, that says, neither the secretary nor blah, 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 anyone working for the Census Bureau will do anything that blah, 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 makes a publication whereby the data furnished by any particular establishment or individual can be identified. Which I call out in part because this was written a long time before differential privacy was defined. But for those of you who already have the definition of differential privacy on your mind, it sounds a lot like how differential privacy was defined. And I'm not a lawyer. I can't tell you that that is what this means. But as we get into how differential privacy has been defined and is going to be used for protecting privacy in the census, keep in mind this is the legal requirement that Census Bureau is operating under when they're thinking about how they must protect privacy. Let me give you a creepy picture that's a reminder to me why privacy of these things are important. This is a map that I found on the UW archives of some maps of segregation that our colleagues in the sociology department were making in 1939. And they have these for lots of different groups. Last time I was giving this talk, I was here. This is Seattle. This is actually a very detailed map of a neighborhood that I live just off the map of in Seattle. And while I don't see people making these creepy maps day to day, it's all embedded in census data. Here overlaid on the old 1939 map is a map that I got off of the Census Bureau's website showing census blocks. So that's why I said thinking of these blocks as actual blocks won't be too far off. And zooming in on that block, here from the Decennial Census of 2010 are marked with little circles, the same style thing, now for the households, where the head of the household is American Indian or Alaskan Native, AIAN, in the census parlance. And I was giving this talk at the Urban Indian Health Institute, which is there in Census Block 1024 of Census Tract 91. So that was like this is the people in the room being mapped in a way that people aren't making a map of, but right there in a table if somebody ever wanted to. So I think, to me, it's clear why there's a moral imperative to protect the privacy in this. There's also a legal requirement too, also for people who want to use it for social research. They need to know or believe that it is anonymous. So, timing-wise, making great time. Feel free to keep asking questions as we go.
If someone cannot read or write, how can they fill the form?
They are allowed to get help filling out a form, and so especially children will have the form filled out by their parents. Not just anyone can help fill out a form. Because of Title 13, it is supposed to be a census worker who helps someone fill out a form if it's not someone from their household. And someone in the census who's doing that is sworn to that Title 13 secrecy. They will not reveal what they found from that person. Other questions? Differential privacy. You've been very patient with me, theorists. Let's talk about theory a little bit. So the most important thing, not for you, this is for if you're talking to social scientists who are nervous about this and they are not clear on what differential privacy is. The most important thing for you to get them to understand is differential privacy is not an app. It's not like a thing you can get from Microsoft and run. Differential privacy is a definition, not an algorithm. And if you haven't seen this intuitive definition of it before, the idea we're trying to get at with this definition is that regardless of external knowledge, someone with the results of this calculation will draw the same conclusions whether my data is in this database or is not in the database. And this is formalized in a paper in part by Anna's student, Frank McSherry, with this mathematical definition that a randomized algorithm A is called epsilon differentially private if, for each possible event P, for any pair of databases that are the same everywhere except for on one person's data, the probability that the algorithm run on one database D gives an event is in P is less than or equal to e to the epsilon, the probability the algorithm run on D prime is in P. I wrote equals because I don't want to talk about the events and sigma algebras and stuff when I'm talking to social scientists. I forgot to change that for you all. But you know what I'm saying. So another know my audience kind of thing. Who has done research on differential privacy? And who's seen this definition before in their studies in computer science? And that is cool. For those of you who are seeing this for the first time, I thought I should prove something. This is a theory seminar, after all. And one cool thing about differential privacy that, even though I've been out of the theory business for a decade, I think I can prove in front of an audience, is the post-processing theorem. And what this says is that if you have an algorithm A that's differential private, and you have any function that takes that output and does something to it, then that composition, the function applied to A, is also epsilon dp. Has everyone seen this before? Is this something that does like yawn to prove, or is this like I'm doing real theory in a theory seminar to prove? I can't tell. I'm going to prove it. I'm going to try. Well, it's a function. It's got a take whatever the output of A is. So what is A? It's an algorithm. You give it a database, and out comes, let's say that it's some n-dimensional real value, but if you wanted something else, we probably could do it with anything. And then F is going to take an n-dimensional real value and give us something else. And we're not saying that it's computable or anything. It's just F's in anything. And this notation, which maybe is a little bit sloppy, means you run A on something, and then you run F on what comes out of it, and that is itself epsilon differentially private. Proof? Well, what is the probability that F of A of D is in some? I forget why I called it P at all. Output? Property? Why? That is the probability that A of D is in the preimage of that property. Property? Is that okay? And that, well, it's just some other event. I can do that for any event. Has my epsilon dp property, because it's A. It's less than or equal to e to the epsilon times the probability that A run on that other database is in that weird set. So bring it back to the other side, and you got it. Preprocessing theorem. I think you can tell I'm very happy with myself for being able to prove something after all this time. Nobody in the School of Medicine wants to prove anything. Or it's a different standard of proof. Now, what is a database? When I'm thinking about this, I have a particular kind of data in my mind, and it looks like this. This comes from the 1940 Decennial Census, where there actually are ledgers where census workers wrote down everything by hand that, because it's been so long since 1940, are now available. You can look at them. And in epidemiology, my colleagues sometimes call this a line list. In health services research, they sometimes call it individual patient data. It's got a lot of different names in a lot of different places. But visually, digitized, it's a bunch of rows, 1.7 million rows. This is probably Washington State in 1940. And each row is a person. And they've got columns for their age and their Hispanic ethnic identity and their race coded in the strange racial categories that they used in 1940, and so on. And so the kinds of things that our epsilon dp algorithms are to do are to count things from data like this. This is a very much of like a health quant kind of example. There's a program called Stata. And if you have never heard of it, you're lucky. It's a data analysis program that is very easy to teach, but it's like a very shallow learning curve that then just hits a wall, and there's no way over it. If you wanted to count how many people were in each county in Washington State from that data, though, you type tab county, and it tells you. And if you are thinking about this kind of epsilon differential privacy for the first time, here is a kind of test your knowledge kind of test. Is this algorithm, count how many people are in each county, differentially private? And just so we know it's real data, like this one down at the bottom, 770, is Yakima. It's a county in Washington State in 1940. The census counted 99,424 people in there. Did you think it was epsilon differentially private? No, it can't be. It's a deterministic algorithm. No deterministic algorithm can be differentially private because when you change the input data, the output data changes. Maybe there's like the null algorithm or something. Yeah, good. I'm back in the theory world. There's one that's That's differentially private. But to make a count like that differentially private, you add noise. Does anyone use R? This is something that I thought also wouldn't come up that much in the theory talk. But this is my attempt to write in this cool new R notation, the way you can kind of pipe data around. And so you tab the county, and then you add noise, and the noise has to have something to do with epsilon to make it epsilon differentially private. And out comes counts that are a little bit different. This table comes from the Census Bureau, so it's a little bit more complicated than tabbing county and just adding noise. And I'll tell you how it's more complicated soon. But the important thing is, in Yakima, where the exact count was 99,424, depending on epsilon, we got something that was a little bit lower or a little bit lower, or as epsilon gets bigger, gets much more and more closer to the value there. This is one part where theorists should know how people take your results and do weird things with them. Everyone in this room knows epsilon is a small positive number. But when you take that out to the theory of the theory department and into the Census Bureau, you got to make sure they know epsilon is positive, first of all. And then they'll do things like say, well, what if we make epsilon 8? Well, no one said epsilon had to be smaller than delta. Yeah, epsilon equals 8 is a legitimate application of this definition. It's just not what we expected them to do at all. And so it obeys a theoretical privacy guarantee, but what? What does that mean? That's not exactly a theory question. That's between theory and applications. We'll throw back to it later. What I want to tell you now is how Census Bureau plans to actually do this for, what did we say, the 10 trillion values that they have under consideration for what they might publish. Because in short, what they're going to do is take geometric distributed noise, which is to say, like the Laplace noise that you might often see in these kinds of things. But let's say we have some count a sub I, where I is between 1 and 10 trillion. That's the precise count. And then form b sub I by adding in geometric noise with some parameter z that's carefully chosen based on epsilon. And if you're not familiar with geometric random noise, the probability that g of z is equal to k is proportional to e to the minus z times the absolute value of k. So it's like a discrete version of the Laplace noise. And that is almost all there is to their approach, except they've made it look very complicated, where they say, create the histogram that's make the 10 trillion measurements, and then add noise to them, and then optimize something. And then people allocate to states, and then optimize something, and allocate it to counties, and optimize something, tracts, block groups, blocks and houses. There's two things that are kind of hidden in this inscrutable diagram that get at what they're going to do beyond just add noise to 10 trillion values. First of all, they're going to do it for more than those 10 trillion values. And they're going to do it in a way that's geographically nested hierarchically. First, they'll just do 500,000 values for the entire United States. And then they'll do 50 times that work once for each state. And then what optimize is getting at is if they just did that, they would be inconsistent. So let me put a L up here for what level we're at. And then they'll optimize to enforce consistency between the 50 times 500,000 measurements for each state and the national measurements. And they want to be able to add them together so that they add up right. Oh, and they want them all to be positive, well, non-negative. No negative numbers of people in any of these histogram cells. And that is in part because they don't want people making fun of them for having negative numbers of people, but also because at the very end, They want to be able to take these histogram cells and turn them into a 300 million row file that is a synthetic file of people, which means they also want them to be integers. So that optimize includes step 1, make everything consistent, and step 2, also make them integers.
So if you didn't do this, you would be actually potentially getting more information by combining, like if you had 2 fuzzy counts, you would, by combining with another fuzzy count, you see they don't add up, you'd be able to kind of get some sense, it would seem, maybe.
And there's a computational limit in here, because they know that with 10 trillion measurements at the block level and still millions of measurements at the higher levels, if they put those all together in one grand synthesis, they'd squeeze the most accuracy out of it. They don't have the computational wherewithal to do it. I don't know how to do it either. And so what they have done by breaking it down this way, this doesn't actually say breaking it down this way, but it's got the same figure that breaks it down this way, is have a natural way to parallelize all of this. And so, for example, all of those 50 states are each broken out into counties, but you can use 50 computers to do each one separately.
We don't really know how to like optimize most things with constraints on like subject to differential privacy. So
Well, the
right.
great
I'm
thing
just
about
saying,
this
like,
is
instead of
post-processing.
Sure.
We've got differential privacy from when we added the noise. So now all of the optimization that we want to do is not going to break differential privacy. I didn't mention 2 important differential privacy things that go into all of this. And if you are getting a first time that you've ever really gotten interested in differential privacy, which is kind of where I am from seeing it used in the census, you will want to know 2 important tools for doing all of this, which I will not try to prove in front of a live audience. But they're both in Frank McSherry's paper. What's this paper called? Frank McSherry's 2009 paper, Privacy Integrated Queries. And they're in other places too, but he lays them out very nicely there. First of all, sequential composition. If you have algorithms A1 and A2 that are respectively epsilon 1 and epsilon 2 differentially private, and you put them together, and figuring out how to say this in concise terms is a little bit of a challenge, but let's just say G of A1 and A2 as a general sort of function that puts together the results of running A1 on something and A2 on something. That will be if this then is epsilon 1 plus epsilon 2 differentially private. This is a fun one to prove. If I wasn't feeling like nervous about proving things in front of an audience, we could probably do this one. Another one that's a little bit of a challenge to write down and to prove, but also a good fun one for you to figure out on your own if you get into this stuff, is the parallel composition theorem. Because this one's totally general, but it adds. If we were a little bit more precise and said that we were going to run A1 and A2 on disjoint subsets, which I'm not really even sure how to write down for these purposes, but A1 is epsilon dp, A2 is epsilon dp, then A1 on D1, A2 on D2, where D1 and D2 are disjoint, is also epsilon dp. And I guess I kind of had that in mind when I was talking about all of this, because I didn't go through the details, but taking a count and adding something to it is epsilon dp. And then doing that for all of these different disjoint counts for the 10 trillion different things that we might want to count in census is parallel composition. That's still epsilon dp. And then putting things together between different levels, well, that's not parallel. There's things that are in the state that are also in the county. That's sequential composition. And so there, we're going to have to add up the epsilon from level 1 and level 2. And that is the art of breaking down the epsilon between these different levels. The convex optimization to put it all back together is, I didn't write it on here. Is it on my next slide what it is? On my next slide it says, write the convex optimization problem in the general form. Do you want to see what it is? We should see it. And I've heard that the video will actually show what I'm writing if I write it over here. So let's try that. So what they're going to do when they've got a sub I for each level is the precise count. They're going to form the B sub I for each level, which is the, what did I call it on the last slide? I just wrote down what it was, right? A sub I plus some geometric noise, where Z is carefully chosen so that it's all going to add up to epsilon.
Maybe use a darker pen.
I can't see that. Maybe I should just go back to the other board where I have that already written down. Yeah, like that. The optimization is going to find C values. And there's a bit more detail in it than seems right to drag you through on a whiteboard. But in short, we want to minimize the sum of squared differences between the CI values and the noisy measurements in the BI values, subject to constraints about the CI values in the previous level, which for something simple, we could just say the sum of the CI values for this level for all the i's is equal to a single C value from one level higher. And that is something they can solve. Oh yeah, we don't want to be embarrassed by having any of these values be negative. So this is, in the sort of econ-y, statsy lingo where the Census Bureau folks are coming from, non-negative least squares, or the way I think about it, constrained convex optimization. We've got a convex objective, we've got a linear constraint, we've got an inequality constraint. We can do that, in theory. A really cool thing that's happened since I was in the theory department and now is we can also actually do that with open source software. And so I was very pleasantly surprised to find not only can we like write on the board this and say there is a polynomial time solution, but we could also head back to our desks and get a computer to do this for 500,000 samples in a reasonable amount of time.
Don't you want to bound the absolute difference of CI, BI?
Yeah, but can you? What would you bound it as?
I don't know, like say the absolute difference is at most some epsilon BI or something, because this you can perturb a BI, like one of the BI is too much.
And that's actually the problem where I'm heading with all of this. So let me show you first, for something where it works well, how this might play out. Because remember the FYI guys column? I told the FYI guy, I know everyone's worried about this differential privacy stuff, but I'll check it out. Like, if they added the amount of noise that they're talking about to the census level, county level measurements that went into your story, here's how things might be. And this is a hypothetical outcomes plot. So the way it's wiggling around is all the different possible values that might have come out of his plot. The story is always the same, that the number change from 2017 to 2018 is going down for the white population, going up most sharply for the Asian population, I was doing this, I told you last week, at the Urban Indian Health Institute, where actually there is a difference between the direction that the Native American bar goes in these different hypothetical outcomes. But for the most part, the story he was telling stays the same. That said, that is not the case in all of the interesting things that people want to do with census data. And so the big open problem right now, which is borderline between theory and practical problem, is how do we tune this up to get something that's acceptable, that's as best as we can get, that's good enough to use. Now, I already alluded to this, but that, by the way, that I was just looking at comes from the American Communities Survey. Census Bureau has promised that they're not going to try to do differential privacy on the American Communities Survey until at least 2025. But we're not talking about 6 questions there. This is a 20-page long survey. It's got 44 questions. The questions have multiple parts. They start with where was this person born. They end with what was their total income in the past 12 months. And how to do DP for this in a way that's going to be acceptable to the social scientists. Huge, huge problem. Not like a nice hand-off to you little problem.
Is race considered a single categorical variable? This is something that I should know, but I don't know the answer to.
Race is going to change, and currently there were 6 categories. Well, there were a bunch of things that you could mark, and it said mark as many as apply. If it's not Latinx, if you're Hispanic or Latino, that's a separate category, ethnicity, yes, no. And then white, black, Asian, American Indian, Alaskan Native, some other race, Pacific Islander, are 6 different categories.
In any box you count, any box you check.
And so those 6 categories are described in any combination, of which there are 63, because you can't mark nothing. So if you mark nothing, they come up with something for you.
So when you were showing the wiggling stuff, what kind of values of epsilon were you using there?
In making this, I simply added geometric noise with epsilon equals 0.01. And so that's basically saying, I'm not going to figure out the optimization. Nobody knows how to do it for ACS anyway. But roughly the amount of variation that they see in the census tracts at this point, based on an experiment Census Bureau did with data from 1940, made me think that would be around the kind of wiggles that we would see. Since then, they actually have run their approach with a proposed set of epsilons that they might use on data from 2010. And so I could go back and update that based on seeing more closely where they might be headed with this. And actually, I've got a few slides that show this, which I'm going to do in 5 minutes or less. Because I told you they ran it on data from the 1940s. And in the 1940s, things were a little bit different than they are in a modern census. They didn't have census blocks, for example. They used enumeration districts. And in 1940, the University of Washington was in enumeration district 41. It was mostly white. And the enumerated value was exactly 1,955 people who marked race as white in the University of Washington enumeration district. For different privacy budgets that they tested out in this early test run, you can see how the size of the population in 4 different runs of the algorithm is different than the exact value of 1,955. For epsilon equals 0.25, which from my computer science days seems like a kind of a large epsilon, you see the kind of variation that they get there. And from epsilon equals 8.0, which doesn't sound like an epsilon at all to my computer science ears, you see that things are much more precise. They're still a little bit varied around that exact value. And for other races that are also in the 1940 census, where the number that was counted exactly is smaller, the variation is still roughly the same size. Although it never goes negative, and that comes back to one of these major problems that when we're thinking about how we might want to tune up this optimization is a major thing we have to take into account. Because going back to how this might work for, say, the AIAN counts that I was looking at when I was at Urban Indian Health Institute, if it works like this, they're okay with it. In the precise count in 2010, in this census block, census tract, there were 5 people, and there were 3110 in the blocks that had more than 0 people in either of these versions. And in the perturbed one, there were 4. So it's a little bit different, but roughly the same, and somewhere in different blocks. However, in many of the other census tracts, there were originally more and ended up with less, including the block around that institute where there were the most AIAN-headed households, and where after differential privacy was applied, there were none. And so this is the kind of like in-between pieces that Census Bureau wasn't really focused on when they were developing their approach, but as they put it out there for people to vet, very quickly became clear, and this is work by Professor Randall Ackey from UCLA, who is particularly interested in what's happening in Indian country, and found that, okay, if you look at the official report on the x-axis, for this is the population size of AIAN alone, meaning they ticked that box for race and no other. And then in this one, what happened in the demonstration product where they applied differential privacy, okay, at this high level, it looks like things are pretty close to the line y equals x. But zooming in here, by restricting the axes just to go up to 5,000, it looks like the points are always below the line. That is to say, the differentially private count is pretty much always lower than the value that was published in 2010. That is bad. And it's nothing intentional. There was no malicious part of this code. They didn't do anything special about AIAN in their code. It's just the way somehow these different pieces have come together in the size of these different values and the optimization and the constraints that has led to this bias.
Instead, rather than thinking about additive squared error, look at some multiplicative term, right? So I'm not saying we should do this, right? But like an additive term of 200 probably matters a lot if you have a sample size of 20, and it probably matters not at all for a sample size of 2 million.
And a lot of the appeal of this approach is when we're very zoomed out and we're saying, so in big numbers, we're going to be very close. But yeah, I think that there's something to be said about like, at some point, you want to focus in more. And on the other hand, for counts of 0 and 1, multiplicative is very hard.
So how much, is this basically a function of this non-negativity, that you've got a small number, you got to have this small amount, sort of less than the value balance, all the possible big things you could add above the value? Is that what's going on here?
It's got to be. It's got to be. But I don't know how to make that precise, let alone fix it. I'll just show you some of the evidence I've got, though, which my colleague in the back row, Beatrix Haddock, put together, which is replicating this work for the urban American Indian and Alaskan Native counts. Because Dr. Ackey was looking at what was happening on reservations. We repeated this work looking county by county at what is happening in the census blocks that are coded as urban, county by county. And we see that same sort of pattern. There's more blocks, there's more noise, but in these census tracts, by and large, when we zoom in, the differentially private output is below the value that the official counts produced in 2010. If we switch this same picture to look at rural, it's above. And so there's some sort of counterbalance here, probably, I think, to do with non-negativity, fixing this up. Question?
What is a dot here? Is it a block?
It is a county. I'll look at Beatrix to make sure I got that right. And so each county has may have urban and rural blocks in it. And this is looking just at the aggregation of the blocks in each county that are considered, in this case, rural. Home stretch, because especially when I give this talk to social scientists who want to use this data, I have really scared them by this point in the talk. I do want to say that privacy in the 2020 census might still be a good thing, and it still remains to figure out the details of how they're going to run it, including details of perhaps how they do things in the optimization, but certainly what epsilon they're going to pick, how they're going to break it up between different levels. And so fundamentally, it's a good thing to know how they're doing this kind of disclosure avoidance. Disclosure avoidance has always been happening since the 1970 US Census. And I didn't tell you about how they used to do it because it's not differentially private, and it's a privacy approach that requires secrecy. So they can't tell anyone how they did it. And if you've taken computer security classes, that is not considered a best practice. Everyone has been operating under the assumption that it doesn't add much error, but we don't know. So a lot of the frustration on the side of data users is from, we didn't know, so we didn't have to worry about it. I guess in theory it's good that you're telling me just how you're doing it, that it's going to help us get more truth, but it has really added to the amount of things I need to worry about. And besides that, we'll know what's happening. We also have an opportunity for releasing more data than has previously been released. For example, all 10 trillion of those measurements could now be published. They're all differentially private. We could even publish the before and after versions of those so that we could say, here's some research data where it says there's a negative number of people. You know, use at your own risk. You have to understand why that is inappropriate in some places and have ways to fix it. But it could be available to researchers to have all of this intermediate data. And there's a gazillion other parts to this, because this is a very stripped down version of the optimization they're really running, that will have to be figured out before they really do it, such as overall epsilon, how to split this between different levels, at each level how to split it between those 500,000 what they call detailed queries, and then other aggregate queries that they bring in as additional either constraints or terms in their objective function for their optimization. Oh my goodness, I went this whole way without saying invariant. Ask a question and then I'll come back to invariant, which is one of the funnest things for theory.
Yeah, so my question is sort of about the definition of privacy. Have they sort of like decided to go with differential privacy?
Absolutely, 100% in for classic epsilon differential privacy. Okay. And so some of the social researchers are like, what other things have you considered? Isn't there anything else you might want to use? And to that, the Census Bureau's answer is like, well, we don't want to use Gaussian differential privacy or Rayleigh differential privacy, these exotic things that computer scientists are excited about, because they aren't established enough. If you have a totally different approach to privacy that you want us to consider, let's talk. We don't know of an alternative to a sort of some variant of differential privacy that we think will be in compliance with Title 13.
One of the benefits, especially in like rural places, is like you could be the only Jew in your high school, for example, right? I'm sure I'm not the only one in this room for whom that was true, right? Like individual guarantees, not just statistical guarantees, are actually quite important.
And that, I think the concordance between the theorem and the statement of Title 13 is what's really appealing to the Census Bureau folks who are thinking about implementing this.
I guess, so my concern was that differential privacy doesn't work that well with correlated data, and a lot of the census data is heavily correlated, like race by location is, there's very strong correlations there.
Yeah.
That you showed in that block earlier with
Yeah,
like,
absolutely.
Jewish population, so yeah.
What else you got?
No, I was just wondering like what sort of privacy definitions.
Yeah, so I think that
Like there's something called dependent differential privacy, which might.
in the next year, I think that they're committed to epsilon differential, like classic, as it was first defined. In the next decade, I think there's room for advancing alternatives that are more appropriate from the direction of differential privacy, or completely innovating in terms of definitions of privacy that might be better suited to this challenge. I can't believe I didn't say invariance, because that is like the most fun, weird tweak on all of this that Census Bureau is doing. Because besides having these precise counts that they're keeping private, having these noisy counts that they're tuning up with optimization, they also sometimes want to publish a precise count. And they call that an invariant because they're not adding any variation to it. But
Doing the countrywide population exactly, for example?
in particular, the Constitution says House of Representative apportionment will come from the number of people in each state. The number of people in each state is not going to have any noise added to it. And so they will have additional constraints perfectly suited to this convex constrained optimization. Throw in additional constraints that say the number of people in Washington state is exactly, precisely the number we counted here. What does that do to differential privacy? No theory for that. We never thought about it until we heard Census Bureau say, well, yeah, of course we're going to do that. The Constitution says we need to. All right. So I'm wrapping up there, and I've had a lot of questions during this, which I appreciate. We'll have a little bit of time for more questions. I want to thank Randall Ackey, who called our attention to this most important thing, ACO grad student Sam Petty, who really helped me understand what's happening with this code, Simpson Garfinkel, Philip Leclerc at Census Bureau. Oh, I didn't add Beatrix to this yet. Also my colleague Beatrix Haddock, who made those graphs about the AIN population. And to close out with a few of the things that are directions as I see it that you could take and run from here if I've interested you, how to formalize DP with invariants. Good thing I told you what invariants were 30 seconds ago. What sequence of partitions will yield the best privacy trade-off? And so what I'm getting at here, I didn't allude to as much as I wish I had, is the way they broke things down to go from the top down was the way they break things down to send out Census Bureau workers who have to go to a single place and walk around that block. We're back in our office with all the data. We don't need to break things according to that geographic hierarchy. Any sequence of nested partitions would be valid for these levels. Is there a better one? What's the best one? Similarly, post-processing optimization. Thanks for the idea to add some kind of constraint on how these deviate. What's the best way to do that? And finally, the real unknown from my perspective that is too hard for me is what do we do for ACS? If you have 44 questions instead of 6, how do you make something that's both private and usable?
What is ACS?
The American Community Survey, previously known as the long-form census. So thank you so much.
So one thing, so the BIs, once you're just basing everything on the BILs, you're totally safe. You could do any optimization that you wanted.
Assuming you don't look at the AIs.
Assuming you don't look at the AIs, but of course we do, I mean, modulo the fact that we do.
Yeah. And that's what's so funny about it is the way differential privacy is set up is like, well, that's somebody else's problem. If somebody leaked the sum of some of these AIs, we protected against it. But Census Bureau has very responsibly said, well, we're the ones who leaked the AIs. We're responsible for that. So yeah, if you don't look at the AIs, you're allowed to do anything you want in post-processing.
So if they're leaking the AIs, are they enforcing that some of the BIs are equal to the AIs and then doing, they're not separately creating a BI associated with an AI that they've already leaked, right?
They're not, and that's part of.
So probably the countrywide and statewide numbers are exact, and then they're only adding noise to like more local numbers.
But they sort of do also. So there's like, I didn't even say DP query. They've got this very confusing jargon. The detailed queries are the 10 trillion values at the most detailed level of disaggregation. They also make these sort of noisy measurements for things that they think might be important, like just the total number of people living in households and the total number of people living in prisons. There's only 7 of those. So those are BI 1, 2, 3, 4, 5, 6, 7, and they add up to the sum of the AIs for all of those that's released precisely because it's the national total.
So particularly about the long form thing, if someone's very concerned about their privacy, they might not want to report their true information, right? Especially since they don't trust the government or something. Like, do you have any thoughts on like how to incentivize people to report their true information?
Oh, the most fascinating thing is bringing the kind of theory of this where it's like, well, what if we prove to them that it will be private, to the social researchers who are like, we'll go ask some people, Professor. And what the social research has shown is that don't even talk about how this is private. Don't even talk about how you've done a good job protecting privacy, because
I'm worried that there was some concern to begin with.
as soon as you've called attention to it, you've made people less likely to answer your questions. No matter how well you promised them you protected it. Yeah, we're better off just hoping they didn't think about it.
Some of the hope too is, right, like the set of things in the short form at least, it's like, okay, these are not things that like necessarily you're particularly concerned about the government knowing about you. Maybe you are, but like at least historically the government can infer these things with like pretty high fidelity. I know.
That's
But,
that's the theory department approach, and the
well,
in
except for,
practice
like-
approach is so opposite that I love it.
Yeah.
It's like we're going to partner with trusted organizations. You know, there's a huge effort right now to get the best count ever of American Indian and Alaskan Natives. They're going through Urban Indian Health Institute and through other trusted partners in those communities to basically go out and make the case. And so when it comes to the privacy tech, the partners who are doing this want to know that Census Bureau is taking this very seriously. They might not tell anyone about it. They like to know in case someone asks them, and they like to know for their own peace of mind. But they're going to go out and work with the communities that they serve to convince them that like this is important, like whatever motivates them based on their own knowing their own community. There's a reason to fill out this information.
But if someone wants to know, can they find out? Like, is it privately private? Or
Like what?
like, if someone wants to know what exactly they're using, like what kind of differential privacy mechanism?
It's public.
Oh, it's public.
Yeah, so that's, anyone can go to GitHub and see the code that they have
I see.
used for their test products so far.
Okay.
It's not like open science where you can see what they've done in the 2 months since they
Epsilon
did it.
value?
But yeah, you can go, I even pasted it into one of these slides, all of the weird config values that they have for how they did one of these versions. Doesn't matter. But yeah, epsilon budget total equals 4.0, split 0.2, 0.2, 1.12, 0.12, blah, blah, blah.
So I know that like Apple does have a privacy budget for some of the things they're sending from their phone. And I remember seeing that the number added up to like 20 or something like that. And I compute e to the 20. It's okay. That's bigger than the ratio. Like
They have
one out of the
computer
entire
science
population
degrees.
of the world.
What's their excuse?
I don't know.
Their excuse is that they're hiring people who know what differential privacy is and begging them to certify what they're doing is differentially private.
But privacy budget of 20.
But so that's
Also that.
well, one important thing about sequential composition, which was written here and then erased, is that it's an inequality. So it's very possible that the epsilon budget of 4.0 is in practice actually much smaller. And that's one of the reasons people have gotten interested in, say, Rényi differential privacy or Gaussian differential privacy, is that the sequential composition theorems you get for those approaches are tighter. In this case, I did some empirics, which would be great one day to see if anyone believes from a theory perspective, to say we've put in invariance, so we could have totally lost privacy. And on the other hand, we've used sequential composition, so we might have much more privacy than what we're finding. And I didn't put in these slides, but I find empirically things are acting like they're in the point, like they're 10 times smaller than the epsilon that's in there, up to a limit. So epsilon of 1 is pretty much the same as epsilon of 0.5, but epsilon of 2 is still really empirically epsilon less than 1.
Let's take the remaining questions offline and thank Abie again.